In this video, we will be discussing about interference. In the last lecture, we saw how interference happens and that it obeys superposition principle, and at certain conditions of phase difference or path difference, sometimes we may get a constructive interference and at times we may get destructive interference. So that was a very general discussion. The interference can be obeyed by any type of wave. But now we are trying to extend the same conclusions to light waves. Understanding what light is was a very long process. First we thought that light was made up of particles, which was propagated by the corpuscular theory. But then later on, Christian Huygens proposed that light is a wave. But we didn't believe him. It was only when Thomas Young performed the Young's double slit experiment we could conclude that light was a wave. Because in this experiment it will be very much clear that light will obey the superposition principle as we discussed in the last lecture. So here the experimental apparatus involves two sources of light and a screen. So let us take a random point on the screen. Let it be point P. So let's assume that a light wave travels from this point to this point P, and a light wave from this source travels to the same point P. We already saw this situation. What will happen at the point P? At the point P, the light from both these sources will interfere and they will obey the principle of superposition. So let this point P be at a distance of x from let this be the center of the screen. So let this point P be at a distance of x from the center of the screen. Let the distance between the source and the screen be capital D. And let the distance between the two sources be small d. So I'm assuming that this point is at an angle theta from this horizontal line, so that as theta changes we can say that the position of this point on the screen will change. So this point can be denoted just by marking this angle theta. As theta changes, the position of the point P on the screen will automatically change. But what we are interested in is to know whether we will get a bright point or a dark point at this point P. This is a light source, this is a light source, and this light will hit at this point and the light from here will hit at this point. But can you imagine that light plus light will give no light at a particular point on the screen? This is nothing but the basic principle of interference, because we already discussed that at certain points or at certain places we may get destructive interference. So if we are getting destructive interference, which means one light wave can cancel out the other light wave. So what are the ways we know whether it will be a constructive or destructive interference? Either we have to know the path difference or we have to know about the phase difference. I think in this case it is better to mark the path difference, because we know the path traveled by the first wave, that is S1 to P, and the path traveled by the second wave is S2 to P. So the path difference here, that is denoted by the delta x, will be equal to the path traveled by the second wave minus the path traveled by the first wave. This will be the path difference. And now if I draw a perpendicular to the direction of propagation, or if I consider that this is a wavefront, which is a common wavefront traveling to that point, from this perpendicular plane, the path traveled by the first wave and the path traveled by the second wave from this point to this point will be the same, which means this distance and this distance is the same. So when we do work out this path difference, the excess path traveled by the second wave will be this part. I'll be more clear on that. This is the path traveled by the second wave, this is the path traveled by the first wave. So the path traveled by second wave minus the first will be this short path. So this is actually the value of our delta x. And if this is theta, then by geometry this will be theta, and if this is d, this length will be d cos theta and this length will be d sin theta. That is by simple geometry. So I can simply say that delta x will be equal to d sin theta. The path difference between the two waves will be equal to d sin theta in this situation. And if this theta is in radian if this theta is small, then I can approximate this as d tan theta. There is no issue in doing that. You can even check with small values in your calculator, but make sure that you put theta in radian. So delta x can be approximated to d tan theta, and from this triangle, you can say tan theta is opposite side by adjacent side, that is x by capital D. So I can write delta x as small d into x by capital D. And now I am rearranging this in terms of x, that is x equal to delta x into capital D by small d. Why did I do this? I now have a general condition of x. X is nothing but the distance of this point from the center of the screen. So if the value of x changes, which means we are looking at different points on the screen. So at what points, or at which points we'll get bright spots and at which points we'll get dark spots? That is my question, which can be clearly indicated by the value of path difference. We already know the condition for delta x, because at this point P, suppose we will take this point P, x equal to d by d and x equal to d by d. I am not writing the value of delta x now, but I can write the value of delta x. I know the condition. If delta x equal to n lambda, that is path difference, if it is an integral multiple of lambda, this is the condition for constructive indifference. So wherever the x value satisfies this equation, there we will get bright points. And whenever the value of path difference is n plus half into lambda, or even you can write it as n minus half into lambda, there you will get a dark point, because n plus half into lambda path difference indicates destructive indifference. So from this very simple equations, you can understand in the screen at certain values of x you will get bright points, and at certain values of x you will get dark points. And how are these points distributed? The value of n will be 0, plus or minus 1, plus or minus 2, because it can be on either side of the screen, starting from 0, 1, 2, 3 can go to this side, also minus 1, minus 2, minus 3 can go to this side. So how are these points spaced? So if I just make a rough sketch of this, alright. So n equal to 0, which means I am trying to plot x over here. So when n is 0, x value is 0. At x value 0, what am I getting? I am getting a bright point. So intensity will be big. Then n is equal to plus or minus 1. When n equal to 1, x becomes lambda d by d. Let this be lambda d by d. At this again I am getting a bright point. Plus 1, then minus 1, that is minus lambda d by d. Here also I am getting a bright point. Then 2 lambda d by d and minus 2 lambda d by d. 2 lambda d by d and at minus 2 lambda d by d. There also I am getting bright points. So at all these values of x, I will be getting bright points. Then what about the dark points? When n is 0, half lambda d, that is 0.5. If this is 0 and this is lambda d by d, then the point at the center will be 0.5 lambda d by d. If this is 1 lambda d by d and this is 2 lambda d by d, here at the center it will be 1.5 lambda d by d. So in between these bright points, I will be getting dark points. So if I plot the intensity pattern, it will look something like this. Here it is 0.5 lambda d by d. Again at lambda d by d bright, 1.5 lambda d by d dark, 2 lambda d by d bright, 2.5 lambda d by d dark, 3 lambda d by d likewise. Similarly, I can extend this side also. So this is the intensity pattern which we will observe on the screen. This is the center of the screen because there x equal to 0. X equal to 0 means it is at the center of the screen. At the center of the screen we will get bright points. Then we will get a series of dark and bright fringes distributed uniformly over the screen. Which means at these x distances, we will get dark points, which means at those points the light from S1 and the wave from S2 are interfering each other and they are getting cancelled out, which means at those points we are getting light plus light, which will give no light, which means we are getting destructive interference. And at these points we are getting constructive interference, which means the light is getting maximized. So this is, here we can't say that at some point light is getting created, at some other point light is getting destroyed. We can't say like that, because this obeys the law of conservation of energy. Energy can neither be created nor be destroyed. What is happening here is just that light energy is getting redistributed. At some points the energy is getting reduced, likewise at other points energy is getting added up. So it is just an indicator of redistribution of energy. And when Thomas Young performed this experiment, he clearly saw that this pattern was observed on the screen. Actually, this experiment he did was with white light. Let's have a discussion about that later. But he observed this phenomenon exhibited by light, which clearly indicated that light was a wave. Because if light was not a wave and if light was particle, then how can it obey the principle of superposition? Just by seeing this pattern on the screen, just by seeing the series of dark and bright fringes on the screen, he was very sure that light must be a wave, and later on it was proved. So this is about the Young's double slit experiment, and from this you can easily calculate what is the width or what is the extension of that fringe, what is the fringe width, how wide is the bright fringe, how wide is the dark fringe. You can easily see from this, because this point to this, that is the fringe width, and this point to this point, that is the next fringe width. And from this you can clearly see that the width of a fringe is lambda d by d. Or you can even approximate that from this equation, because the fringe width, it is represented by the letter beta. This is the general equation by which you can, this is the, okay, if I am taking the first bright fringe, then this will be the second bright fringe. So the distance between the two fringes, and that will be the width of a single fringe. And from this you can write it as, if I substitute n plus 1 over here, n plus 1 lambda d by d minus n lambda d by d. And if I take lambda d by d common, lambda d by d n plus 1 minus 1, which is, n plus 1 minus n, which is simply lambda d by d. The fringe width is given by the equation lambda d by d, which can also be easily seen in the intensity variation pattern. But I missed out a very important thing. I told you that we are considering two sources. If you take two sources and perform this experiment, you will not see any fringe on the screen, because these two sources will not obey the condition for obtaining dark and bright fringes. What was the condition? We discussed in the last class that for obtaining bright and dark fringes, what was the condition? The frequency should remain same, and if there is a phase difference, that phase difference should be constant. And such kind of sources are called coherent sources. Such kind of sources are called coherent sources. What are coherent sources? Their frequency should remain the same. Also, if there is a phase difference, that phase difference should be constant. If these two conditions are obeyed, then we can say that the sources are coherent, and we can never obtain two different sources which can obey these conditions. And the reason for this, I already told you. I'll do a separate video on coherence. In that you will understand a bit more on why this is happening. But in order to make these two sources coherent, what we do is that we actually place a single source, and we'll just keep a screen over here or a blind over here, and we'll put two holes over here, and we'll let the light from the source fall over here, and the same light from the same source fall over here. So what we actually do is we will derive the sources S1 and S2 from the same source. So obviously the frequency will be same, because there is only a single source. It will have only one frequency, so the frequencies will be same. And even if there is a phase difference, that will be constant, because whatever phase difference happens in S1, that will be reflected in S2 also. So they will be locked in phase. So instead of using two sources in Young's double slit experiment, experimentally we achieved this condition by using a single source and deriving the two sources from this single source. This is about the Young's double slit experiment.